All right, so let's take a look now at how we actually make buffer solutions of a target pH or a specific pH. And the first thing to note is that a solution can only be a buffer solution if it has the ability to resist the pH change when either an acid or a base is added, right? That's how we define a buffer. If the concentrations of the weak acid and the conjugate base differ by more than a factor of 10, the solution doesn't have that capacity to act as a buffer, right? So what that means is the ratio, let me rewrite this here, the ratio of the concentration of the conjugate base to the weak acid, okay, has to be between 10 and 0.1, right? So if they differ by more than a factor of 10, that solution cannot function as a buffer. So what that means is the log term in our Henderson-Hasselbalch equation, so the pH equals pKa plus log of the conjugate base over the acid, right? What this means is that this term here cannot be more than 1, or can only have values from -1 to 1. Okay, -1 to +1. And the pH of the buffer cannot be more than 1 pH unit different from the pKa of the weak acid. And that's known as the range of the buffer, okay, where the pH is equal to the pKa plus or minus 1. So what this means then is that it allows us to select the appropriate conjugate acid-base pair to prepare a buffer with a desired pH, right? So the first thing that we'll need to do is to pick a weak acid where the pH is close to the desired pH. And then what we can do is we can substitute the pH and the pKa values into the Henderson-Hasselbalch equation in order to determine the ratio of the conjugate acid to the conjugate base to the weak acid, and then we can calculate the molar quantities afterwards. Okay, so this all starts with picking a weak acid where the pKa of it is close to the desired pH. Let's take a look at an example. Okay, so it says select an appropriate weak acid from the table at the right and describe how you would prepare a buffer with a pH of 9.50. Okay, so the first thing that we need to do is we're going to take a look at, we want a buffer here with a pH of 9.5. Okay, so we're going to select a weak acid that has a pKa that is fairly close to 9.5. So if you scroll down, we can see that the ones that are closest to 9.5 would be the very last two down here. Okay, so we have HCN, which is hydrocyanic acid, or we could have picked, we could by the same token pick phenol that has a pKa of 9.89. Okay, so let's just for simplicity's sake, we'll just take the phenol one, 9.89, which is a little bit higher than the 9.50. And what we're going to do is substitute it now into the Henderson-Hasselbalch equation. Okay, so we have our pH, which is 9.50, is equal to the pKa, which is 9.89, plus the log of the concentration now of the conjugate base of this, right? So C6H5OH, when this acts as an acid, right, will give up the H plus, and then the conjugate base would be C6H5O minus, right? So the conjugate base there would be the C6H5O minus, and then the acid there would be the C6H5OH. right? So if we rearrange our equation, we bring this over to the left side, we have negative 0.39 would be equal to the, let's see here, the log of the C6H5O minus divided by C6H5OH. Okay, so this is log to base 10. So the way that logs work, we take 10, we raise it to the negative of the other side, 0.39. Okay, we end up with the ratio now of the concentrations of the conjugate base of phenol and phenol itself. Okay, so if we evaluate that, that gives us 0.41. So what this tells us is the ratio of the conjugate acid, I'm sorry, the conjugate base to the acid is 0.41. So the ratio, in other words, of the conjugate base to the acid is 0.41 to 1, right, in terms of the concentrations. So, for example, if I have a liter of, and this is to make the comparison simple. So, for example, in 1 liter of the buffer, what you would dissolve is 0.41 moles of the C6H5O minus salt, right? So you can't just have a beaker or a container of the anion. It comes in a salt form. And 1 mole of the acid, C6 phenol, C6H5OH. So in that 1 liter, right, we have 0.41 moles, that's 0.41 molar. To 1 mole of this, that's a 1 molar. So that ratio will be 0.41 to 1. Okay, so that's how we use the Henderson-Hasselbalch to determine how we need to make a buffer of a specific pH. Now, we could have also used the HCN, the hydrocyanic acid, by the same token. However, we'd probably want to use the phenol because hydrocyanic acid does have the cyanide ion in it. That is fairly toxic. We would want to avoid using toxic substances if we can avoid them, but it could theoretically still be used.